Okay, let's continue with example 4. Use a rational function model. This is an application word problem, so we'll look at an example of a word problem. The cost of moving a pollutant is modeled by the given function where f of p is the cost in millions of dollars of removing p% of the pollutant. What percent of the pollutant can be removed for $78.3 million? So if you look at this function, it's a rational function model, right? And we know that p is a percent, so we have a restriction other than the domain and range of the graph itself. So in real life, we have more restrictions to think about because, for example, like percent, we know it has to be from 0 to 100. And for the cost here, it has to be positive. We can't have negative cost in this situation. So in a word problem like this, there are going to be a lot of different factors that you have to think about in order to figure out the reasonable domain and range. So even though we have a rational function where we have different curves, we may only use part of it. So for example, if you graph this equation, you'll be able to see different curves. So this one, this curve, so we have a rational function that has the two different curves here, right? But in our situation, this function represents the cost, and p, which is our domain, represents percent. So our domain has to be between 0 to 100. It cannot be over here, greater than 100, right? So we're not going to even use this part of the function. So we're only going to use when p is equal to 0 to 100, right? And then we're not even going to think about negative p and negative values for f of p. And so we're only looking at the values here, okay? And so looking at this, what percent of pollutant can be removed for 78.3 million? So this is our range, right? Value of our f of p, not p, right? So we want to figure out p% when f of p is 78.3. So we can easily figure it out by plotting the graph, right? What are we looking for? 78.3 million for f of p. So we're looking at the y value to be equal to 78.3. Oh, there it is. So when p is exactly 90, our y value is 78.3 exactly, right? So you can also create a table using this, and then in Desmos you can't really plug in the y values yet, y values first. So you can double check by looking at your x value, 90. When p is 90, your f of p is 78.3, so 78.3 million. So this is one way to figure it out. If you have a graphing calculator with your device, then you can graph two different functions. You can graph the rational function here, and you can graph another linear function when when y is equal to 78.3. You'll be able to find the intersection. Yeah, so the point 90,78.3 would be our solution, which in real life, if we interpret our solution, will be 90% of the pollutant should be able to remove for $78.3 million. Okay, not too hard, right? So in real life, you do have to think about other factors that really make sense. Let's look at try number 4. New techniques have changed the cost function. Instead of our original function, we have the new function g of p that's equal to 3.2 p plus 1 over 100 minus p. What percent of the pollutant can be removed for $50 million? So pause the video, see if you can solve it by yourself. Come back when you're ready for answers. Okay, are you ready? All right, so you can look at this function and graph it and see how the graph looks like. Let's graph our new function. And so our new function looks like this. And again, we're going to use our reasonable domain and range, where domain is going to be from 0 to 100. So we're going to use this part, okay? This part of the graph. And so we're looking at when we have $50 million. So when y is equal to 50, how much percent is it going to be? So yeah, we have 94, 50.3, 93.97, 50.034. So that's really close to 94. We can check by table. 93. Why isn't this coming out? So yeah, we looked at 93. Oh, okay. Maybe I should use f of p, maybe. Yeah, there we go. Okay, 93 versus 94. Which one is closer to our answer? 50 million. That would be 94. So we can say about 94% would be our solution. So 94% of the protein can be removed for $50 million. Okay, that was try number 4, example 4. Let's look at our last example, example 5, graphing a rational function. So our goal for this lesson is to graph a rational function. And we looked at graphing some rational functions in previous examples, but this is the last example to look at. So for example, if we have a more complicated graph, not just 2 curves, but maybe multiple curves, right? So for example, we have an f of x that's equal to 4x squared minus 9 over x squared plus 2x minus 15. So the steps are still the same. We're going to determine any asymptotes by looking at the graph. So vertical asymptotes could be figured out by factoring our polynomial in the denominator. So factor out x squared plus 2x minus 15, and we're going to get x plus 5 and x minus 3, and either negative 5 and 3 would make a 0 for our denominator. So those would be our vertical asymptotes. And then we'll see the horizontal asymptote by looking at the degree. We have the same degree, so our function is going to get closer and closer to 4 over 1. So that will be our horizontal asymptote, y equals 4. So we have the vertical asymptotes x equals negative 5 and x equals 3, and horizontal asymptote y equals 4. We have 3 asymptotes. So we're going to start sketching the graph by plotting the asymptotes first, and then the next step is just to choose some x values and plug it in to figure out our curves. So yeah, you'd have to pick a good number. Obviously, your graph cannot go over your asymptotes. So for this curve right here, it's either, if you figure out x equals 0, you have 0.6. So you know your graph is going to be in this section, and it's not going to go over here, right? Or here or here. So you know this graph is going to be here, and your rational function will always have a diagonal curves on the diagonal section. So you know the other curves will be here, but just to make sure, plug in some points to make sure that your points are on this side of your graph, okay? Yeah, so it doesn't have to be super accurate with your decimals, obviously, but you do have to make sure that your curves are in the right region from your asymptotes, from the sections that you divided with your asymptotes, okay? All right, let's look at try number 5. This is going to be a weird graph, but you can do it. So let's identify the asymptotes and sketch the graph of g of x here. Follow the same steps and you'll be able to sketch the graph. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? All right, first of all, you need to figure out the vertical asymptotes and any horizontal asymptotes, right? So your vertical asymptotes is when your denominator is equal to 0. And if you factor this out, you'll have 2 times x squared minus 5. And how do you solve for 0 here? Well, you have to make sure x squared minus 5 is equal to 0. And then x squared is equal to positive 5. And so x is equal to plus or minus root 5. And this is a real number. And so your vertical asymptotes are at x equals plus and minus root 5. And so you have 2 vertical asymptotes, and then see if you have any horizontal asymptotes. You do have the same degree, and it's going to get closer and closer to 1/2. But in this case, you have a weird function. When you can factor it out, let's see if you can factor out the top part, okay? So if you factor out the top part, you'll get x times 6, right? Times 6, x plus 1. And then you'll be able to get that. Yeah, and then you have this. Yeah, so comparing your x values, the bigger your x gets, right? You have x squared minus 5, and then x minus 6 times x plus 1. So looking at your factored form, you can plug in and easily figure out your y values. So first of all, so in this case, you will not have horizontal asymptote, but you'll see why when you graph it, okay? So possible horizontal asymptote is 1/2, but because the degree is the same, but this is a weird function. So look at your vertical asymptote. You'll have about 2 point something. So let's say this is positive root 5. And then this is negative root 5. And then if you plug in 0, you will get 6 over negative 10, right? So that's that's negative 0.6. So maybe over here. And then you plug in some other numbers, you'll see that, oh, it goes over here. And so maybe I'll have a curve like this, but no, really, you have to plug in some points accurately, and you'll see that as it gets closer to root 5, you will see that your fraction will approach to positive infinity. So the speed of the numerator will increase a lot faster than the denominator as it approaches positive root 5 from your left, and it goes to the positive. So it almost have two curves like this. It doesn't really go down, but like, yeah, it has a different end behavior. So in the middle, you have a weird graph where your end behaviors are not in the same direction. And then on the other side, you have a curve that looks like this, and then another curve that looks like that. So in this case, yes, those two curves at the very left and at the very right will not reach 1/2. So you almost have a horizontal asymptote here, but then because of your middle curve that actually goes up over here, we'll be able to have 1/2 actually. So yeah, 1/2 is possible once, and then yeah, and so you will not have an horizontal asymptote in this case. So it is important to be able to graph just in case you have a weird graph like this. Okay, so let's summarize our lesson, graphing rational functions. Remember that a function that's expressible as a fraction with polynomials in the numerator and the denominator is called a rational function. So this is the definition of a rational function. And you need to have polynomials on both the numerator and the denominator. And you'll be able to figure out vertical and horizontal asymptotes to graph your function and to be able to see where your end behaviors are approaching. And so in order to figure out vertical asymptote, you have to see where your q of x, where the polynomial in your denominator is equal to 0. And your horizontal asymptote is when your graph is approaching but will never equal to that number. So you'll see generally it'll follow this rule where if it's less than the degree of the denominator, horizontal asymptote is at y equals 0. And if it's greater than the denominator, there's no horizontal asymptote. And if it's equal to the degree of the denominator, you set y equal to the ratio of the leading coefficients, and the graph of the line is a horizontal asymptote. And so this is an example of a function, of a rational function and a graph. So we learned how to graph rational function in this lesson. We'll continue with the next lesson in the next video. Bye!